Hey everyone, so today we're going to work on applications of differential equations. Okay, so the first thing we're going to actually talk about, and in general, we talk a lot about exponential growth and decay. So there is a general equation for this that we actually did in Algebra 2, but we haven't written it as a differential, so let's try that and kind of get a general idea of an equation we can use for some of these problems. So the rate of change of y with respect to time, so dy with respect to time, dt, is proportional to y, is equals proportional. If you guys remember, again, back to Algebra 2, we used like a constant of some sort, so k is proportional, so k times y. Find the general solution for y. So at this point, once you've got this written, and if you notice that you have other equations like this coming up, like number 1, we'll actually use what we get as an answer here. So what you want to do, we're going to divide y over, multiply dt over, and we're going to solve for y, like we've been doing. So this would be natural log absolute value of y equals kt, since this was t to the 0th power, t to the 1st, plus c. Okay, we, from this step, remember, you can kind of wrap around and rewrite this as an exponential. So e to the kt plus c is equal to the absolute value of y. Get rid of the absolute value, plus or minus e to the kt plus c. Okay, and that's kind of it. The main thing I will tell you is this is typically rewritten a little bit differently. If we rewrote this as plus or minus, remember this property, e to the c times e to the kt, exactly the same thing. You'll see it written sometimes where it will say like let a equal plus or minus e to the c. E to the c, I mean c is some made up constant. E is a number, so this is just representing some other constant. So we can just use the letter A or whatever letter you choose. So we've got this equation, A e to the kt. Okay, and this might look like, if you remember back in like Algebra 2, we did like P e to the RT, like PERT, that equation for continuously compounding interest. So this is also still exponential growth and decay. Exponential growth and decay. And since we derived this equation, we're welcome to use it. Like on the next problem, we're actually just going to grab this and use it versus starting the process over. But you're welcome to always start like this, and we know we can get to this answer. Just a side note, typically A, or whatever that value is there, A is initial value, or the value when t is 0, and y would be like a final amount or value. Okay, so that's not always, I mean, that's just, I'd say, typical if we see this setup. This would be the initial amount. You know, there was $5. We want it to grow to $10, whatever that may be. So that is what we're going to use. So take a look at number 1. Once you've got that written down, very important right here. Okay, and it says, suppose there's 10 grams of plutonium isotope Pu-239 was released in the Chernobyl nuclear accident. If Pu-239 decays according to the model given by this differential equation, dy dt equals negative ky, and its half-life is 24,100 years, how long will it take for the 10 grams to decay to 1 gram? Okay, so first of all, we have this dy dt equals negative ky. So we could use that, start this whole process, blah, 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 get here. Notice the only difference is that this is going to end up being y equals a e to the negative kt. So since we already did the work on that, let's just use it. And you're welcome to do that since we already have that process written. We're going to use this equation. The first thing we have to do is solve for some of the constants. And so we're going to use what we have to solve for k. All right, it says the initial value was 10, right? So 10 grams is the initial value, so we can fill that in for sure. Okay, we want to know when we'll get to 1 gram, so 1 equals 10, but we're missing this k value up here. So we're actually going to solve for k first, and we're going to do that by using some of the other information. It says it's half-life. Okay, that's how long it takes for it to drop to half the amount. So here's really what it's saying. When will 10 have a final amount of 5? Okay, and specifically, it will happen, t is now 24,100. Okay, so we can solve for k. We plugged in a final amount. If we started with 10, half-life of 24,100. We would get 5 as our final amount. So now we have everything filled in except k, so we can do some algebra here. Divide by 10, 1/2 equals e to the negative 24,100k. And then natural log both sides, or technically rewrite it as a log. So take the natural log of both sides, natural log of 1/2. Remember, natural log of e cancels, and we just get negative 24,100k. Divide by that lovely number, and we get k equals natural log of 1/2 divided by negative 24,100. Okay, negative 24,100. So here's our k value. It's really fun. Don't plug it into the calculator yet. I know it might be tempting just to use a decimal because you don't want to deal with this weird fraction, but then you'll have rounding errors and we don't want to deal with that. So you're going to take that, let's plug it in. So our actual, or like let's call it specific equation here would be 10 is the original amount, e to the negative k, which is now natural log of 1/2 over negative 24,100 t. All right, the negatives would cancel here. So you could rewrite this as 10e to the natural log of 1/2 over 24,100 t. And then finally, now we're going to answer the question. So the reason that these are difficult is because it has a lot of algebra going into it. Your algebra 2 skills have to be pretty strong in order to get to this step. But once you're here, now we're just solving for, let's see, it says how long will it take? So what is t? If I have 10 grams to start, we already have that in our equation. When will it decay to 1 gram? Okay, so you're solving here. I'll write in pink. 1 equals 10 e to the natural log, like the final amount being 1/2 over 24,100 t. All right, so we would divide by 10. 1/10 equals e to the natural log of 1/2. Just carry around that fraction forever there. And last step here would be we could take the natural log of both sides again. Okay, natural log of e cancels. So I get natural log of 1/10 equals the natural log of 1/2 over 24,100 times t. Okay, to get rid of this guy, we could just multiply by the reciprocal. Algebraically, that will cancel, right? So that's what we're multiplying this side by. So you are going to get, let's see, t equals, we had natural log of 1/10, and then we're multiplying by 24,100 over natural log of 1/2. So we could just type that. This would, of course, be a graphing calculator problem. So feel free to type it in your calculator, see if it matches with mine. And you should get, let's see, it's 80,058.467 years. So that's how long it would take 10 grams to decay to 1 gram for this specific PU239. Okay, we always round to 3 decimals unless otherwise specified for AP. Let's try out one more. All right, so take a look at the next one. The next one's talking about rate of bacteria growth is proportional to the square root of time. So this is not exactly just the original equation we were talking about, that AE to the KT. So what we're going to use is actually just rewrite this. So B is going to be the bacteria, T is time. So the change in bacteria with respect to time, it said it's proportional, so K times the square root of time. Okay, so again, you might guess we need an original equation for B, and first we'll get a general solution, then we'll solve for C, solve for K, etc. Then we'll find the final answer. So you're about to dive into all the algebra to get our kind of final equation for B, where we can just plug in what is, B of 7 for the final answer. So we're going to split up those variables. Let's see what we got. dB is equal to K. This is rewritten as T to the 1/2 if you want. dt. We get B equals, this would be K T to the 3/2 times 2/3 plus C. So that's a great start. That is technically the general solution. And so now we need to find C, and we have to solve for K. So you should be solving for C first. Okay, so solve for C so we can get a particular solution here. What other information do we have? It says the initial size, so when T equals 0, the bacteria population is 500. So you have t equals 0 and b equals 500. We also have the second sentence, which says after day 1, when t is 1, b is 600. So we'll use that as well. But let's start off with this first one, since that will help us. So we're going to solve for c here. Okay, I'll do this in green. T equals 0, b equals 500. So this equation now would read 500 equals 2/3 k times 0 to the 3/2 plus c. Okay, this is 0, so c would be 500. Okay, so you take one more step. Now I have b equals 2/3 k t to the 3/2 plus 500. All right, next constant. Okay, now you want to solve for k. So we're going to use that next piece of info. It says after 1 day. So I'll write solve for k so we know what we're doing here. We're going to use t equals 1 day, and the bacteria was 600. So typically to find the constants, you'll get either an initial condition or you might get just a different given condition, and we'll use that to solve. First, the only two variables missing should basically be those original variables. So in this case, b and t. Everything else we want to solve for and make sure we're ready to go to plug in. So 600, I'm going to use this. 600 equals 2/3 k, 1 to the 3/2, which is just 1, plus 500. Okay, subtract 500 from both sides. 100 equals 2/3 k. If we multiply both sides by 3/2, okay, we would get k equals 150. All right, so there's our two constants. Last but not least, we are going to rewrite the equation one more time so that we can get a final equation for b. Again, these are just really algebra heavy. There's some calculus obviously going on like here at the beginning, but a lot of it is just algebraically not making mistakes, so just be careful. So we have b equals 2/3, k is 150, t to the 3/2, and then we have c is 500. We can multiply these two together, which would give me 100, t to the 3/2 plus 500. Okay, so this is the equation I'm going to be using, and the very, very last thing is we actually get to find the answer. So it's the approximation of the population after 7 days. So b of 7, or you could just say b equals 100 times 7 to the 3/2 plus 500. You get out your calculator, you can type that right in, and you get 2,352.026. Remember, this is a bacteria size, so we shouldn't really have, it's a population size, we shouldn't have a decimal. So we'll just say approximately 0.026, so 2,352 bacteria in the population here after 7 days. All right, so that's about it. Make sure you feel comfortable with the idea of getting here to here, and also make sure you feel comfortable with the first problem we did where we solve for y, and we get that a times e to the kt. We will try number 3 in class. Let me know if you have any questions, and thank you for watching.